So we have MnO4 -1 and we have DE. And the other thing was we have OH -1, right? And the products in our case are MnO2 plus DeO3 -2, MnO2 plus DeO3 -2. And what else? There is water. So let me check if this equation is copied correctly. The MnO4 -1, DE, right? That's fine. So it's this equation. So we need to balance this equation. So what is the oxidation state of Mn over here?
7.
So over here it's +7. D is obviously 0. O is -2, H is +1. So that's
It is
every.
1. Yeah, and 4 and 4.
So this is 4. This is 4. So who's D is the one going from 0 to +4. So that means
Oxidized.
lost 4 electrons, right? And Mn goes from +7 to +4. So that is a gain of 3 electrons, right? So,
Yes.
so what do I multiply both numbers? I mean, this should be multiplied by what?
By 4.
And this other one should be multiplied by
3.
By 3. There should be 4 Mns and 3 DEs. So that part, the number of electrons gained and lost are now balanced. So there should be 4 Mns and there should be 3 DEs. And the last thing is we need to balance water. So we've got just a second. We've got how many hydrogens on this side? We've got 2 hydrogens. So let me make 2 hydrogens on the left side as well, right? So on the right side, we had 2 hydrogens. Are the oxygens balanced? That's 4 plus 4, that's 16. And 2, that's 18. So you have 4 into 2, 8. 8 plus 9, what is that? 8 plus 9 is 17. And there's 1, so it's balanced. Is this clear?
Yes, sir.
So, so you've balanced both equations. So let's move back to our, and let me just quickly check the other ones as well. So you did 4 pH3 plus 12 H plus 1. And in the other one, you had 8H plus 1. Don't you think this method that you're working on, isn't that slightly more difficult?
Yes, I realize. Yes, sir, it is difficult, the one I'm using.
I mean, like, you have to be like really quick. Like if I do the IO4 -1, right? And I think the other one is pH3. Like you don't have to make 2 separate. I mean, basically you just it's IO4 -1 plus pH3 and they produce I -1, right? And what else is produced? P4 and H2O, right? I mean, this is the reaction, right? So you need to balance this. So what is I over here? It's +7, right? And over here it's -1. So basically it's a gain of how many electrons? 8 electrons, right?
8 electrons, yes.
And P is, I think, -3. And it goes to 0, right? So that's a loss of how many electrons? It lost 3 electrons, right?
Yes.
So again, it's 8 and 3. So what could be the common? Like I can turn this into 24. So I need to multiply this by 3.
3 multiply that by 8.
8. So basically, I need 3 iodines. So 3 iodines and 3 iodines over here. And I need 8 phosphoruses. So 8, multiply this by 8 and multiply this by 2 because I just need 8 phosphoruses. So that would make it 8, right? And that's pretty much the equation is balanced. The only thing you have to do is you've got hydrogens. That's 8 into 3. That's 24. So that's going to be 12. So that's it. Is this clear?
Yes, I think I'll use this method. It's much quicker.
Yeah. So just remember, you have to save time. Like you can't because this is going to be something that's very basic. You have to be very quick with this. So coming back to this is what we were doing. What we were up to was that we said that we wanted to figure out who's going to lose electrons, who's going to gain electrons. Like, how do you make the equation? So you have standard electrode potentials. For example, sodium, we know that it wants to lose electrons. So sodium metal atoms would quickly start forming sodium ions, lots of them, and lots of electrons are going to be produced. A lot of negative charge is going to accumulate, and the potential that's going to build up over here is going to be a negative potential, which can be measured. And it's not going to happen endlessly. At a certain negative potential, the ions will start getting attracted back to them. So there's going to be a reversible reaction. So is this all clear?
Yes, sir.
And once that reversible reaction happens, the potential becomes constant. It no longer changes, because every time sodium loses electrons to form sodium ions, the negative charge increases and it attracts another sodium ion from somewhere else, which gains the electron back. So it's to and fro, it's going to and fro. So I wanted to discuss, so remember, this type of electrode is known as a metal aqueous metal ion electrode. So that's type number 1. It's a metal aqueous ion electrode. What that basically means is that whenever you have a metal and you're trying to figure out whether it wants to form ions, or you have ions that are turning into metals and you want to figure out what is the electrode potential. So you're going to make an electrode similar to this. The ions would be in the solution, and the metal electrode would be, the electrode would itself be made up of metal. Is that clear? Raji, is this clear?
Yes, sir.
I mean, so one example is, if somebody is going to ask you what happens if you have copper, but let's talk about electrodes in a bit. Let's talk about the other type of electrodes. So here's another electrode, and this time what I'm trying to figure out is, I want to figure out, does Cl2 like to gain electrons, and does it like to form Cl ions, or is the reverse going to happen? What do you think is going to happen? Is Cl2 likely to go in the forward direction? Does it like to gain electrons? Or would the Cl ions start to lose electrons? What does it want to do? What do you think? Does it like to
form negative ions?
It likes to form negative ions. Like, most of the time you see Cl in the form of these negative ions, like NaCl, that's Cl negative. So Cl basically wants to form negative ion. It wants to gain electrons. So what you're going to do is, you're going to set up an electrode, and we're going to try and figure out what does it want to do. So there's going to be this gas jar, because Cl2 is a gas, and the Cl2 gas would be entering this gas jar. And the solution will contain a lot of Cl ions. So there would be Cl ions that would be part of that are going to be part of the solution. And they're going to be aqueous. Now, if Cl2, now there is no electrode. I mean, you need a source of electrons. Like, if electrons were going to accumulate, there should be some metallic substance over here where the electrons would accumulate, right? Now, in this case, both of them are non-metals. So if Cl2 really likes to gain electrons, where would it gain those electrons? There's no place for it to gain electrons. So what you're going to do is, you're going to add a platinum electrode. You're going to add a platinum electrode, which is an inert electrode. So you will add a metallic substance, and you'll take that metallic substance and connect it to a voltmeter, so you can also measure the potential on that metallic substance. And you'll connect it to a reference point. Now, we know that Cl2 is going to come in, and Cl2 molecules are going to come in, and they're going to start gaining electrons. So let's say you have a Cl2 molecule that is coming into the gas jar, and here's a Cl2 molecule. And what that Cl2 molecule would do is it's going to gain electrons. It likes to gain electrons. So it's going to gain electrons, right? And there would be other Cl2 molecules in the gas jar, and they would also start to gain electrons from the metallic rod. Remember, the metallic rod has lots of delocalized electrons, so it can lose electrons, right? Is that clear? Rajni, is this clear?
Yes, sir.
So the Cl2s are gaining electrons. So the metallic rod would become positively charged, because the metallic rod would start to its delocalized or sea of electrons would slowly get depleted. So it's going to have fewer and fewer delocalized electrons, and it will become positively charged. And a lot of Cl lines are going to be formed in the solution. But this would happen up to a certain point. So initially, all the Cl2 that it would do is it will try to gain electrons, constantly gain electrons, and it would try to form Cl-1. But at a certain point, the positive charge, the metallic platinum electrode would become so depleted, and there would be so few electrons that initially it was forming Cl lines, right? But then it would start pulling electrons back from Cl lines, because the positive charge would become so large that it would start pulling electrons back from Cl lines. And that is when the reversible reaction would get established. Is that clear?
Yes, sir.
So, and at this point, the potential would, there would be a certain potential that would become constant. And in this case, it's going to be a positive potential. It's going to be 1 point, I mean, the data booklet gives us 1.36 volt. So that's a positive potential. So whenever you have a substance that likes to gain electrons, the metallic electrode over here would become electron deficient. It would become positively charged. And whenever you have a substance that really likes to lose electrons, the metallic rod would have too many electrons on it, and it would become negatively charged. So is the idea clear?
Yes.
Now, this specific electrode that I drew, that's a gas plus aqueous electrode. Just a second with me. So this specific electrode that we constructed, that's I don't know why this. So this one is specifically a gas. Whenever you have a gas, you're going to have a gas jar, and there's going to be a platinum electrode. And now there's a third type of electrode. The third type of electrode is, what if you have aqueous ions only? What if I want to figure out this relationship? Like, I've got Fe3 plus. I want to figure out, does it like to gain electrons and form Fe2 plus? So does it like to go in the forward direction? Or does it like to produce electrons and lose electrons? So if both of them are ions, what I'm going to do is I'm going to construct an electrode. And this time, since both of them are ions, those ions would be part of the solution. So the solution will have Fe3 plus, the solution will also have Fe2 plus. Now what I have to do is, if Fe3 plus likes to gain electrons, where would it gain those electrons? So there must be, or Fe2 plus wants to lose electrons, where would it lose those electrons? So there's got to be a metallic electrode that needs to be introduced, and that metallic electrode is going to be made from inert platinum. So if Fe3 plus or Fe2 plus really likes to lose electrons, what will happen is that a lot of electrons would accumulate on the metallic electrode, because Fe2 plus would start to produce electrons. On the other hand, vice versa, if Fe3 plus likes to gain electrons, so Fe3 plus is going to gain electrons from where? From the metallic rod, from the sea of electrons that are present over here, and the metallic rod would become electron deficient. Whatever happens, at the end of the day, there's going to be a reversible reaction, and the potential that's going to build up is going to become constant. And you're going to go and measure the potential. In this case, yes. Yes, what's the question?
I don't really understand what happens in this case.
Nee, I'm just saying that what if I want to figure out, does Fe3 plus want to does it want to gain electrons to form Fe2 plus, or would Fe2 plus lose electrons to form Fe3 plus? I'm trying to investigate what's going to happen, right? So since both of them are ions, I'm going to add both ions to the solution. Is that clear up to this point?
Yes.
And now I'm going to try and figure out, maybe Fe2 plus really likes to lose electrons, right? Let's hypothetically speaking. Let's say that Fe2 plus has a very high tendency to actually lose electrons. So that means it's going to produce a lot of electrons, right? So what will happen to the platinum electrode? There would be a lot of electrons that would be produced over here. Is that clear?
Yes.
And your electrode potential would become negatively charged because it's going to be a negative potential because a lot of electrons are going to be produced over here, right? Or vice versa, maybe Fe3 plus has a very strong tendency to actually gain electrons to form Fe2 plus, like it wants to go in the forward direction. So Fe3 plus has a very strong tendency to gain electrons. So Fe3 plus would start to gain electrons from the metallic rod. And if it starts to gain electrons from the metallic rod would become electron deficient, and there's going to be a positive charge on that. Is that clear? So whatever happens, at the end of the day, there's going to be an equilibrium established, because remember, the reactions are not going to go in one direction. At a certain point, the charge that is going to build up over here would be so large that the reverse reaction will start, and both reactions would reach equilibrium. Is that clear?
Yes.
So anyway, so just remember this point, that when you are trying to investigate ions and you are trying to figure out whether it likes to gain electrons or whether it likes to lose electrons, you put both ions into the solution and you introduce a platinum electrode. Whatever happens, the potential builds up on the platinum electrode, which in this case is 0.77 volts. Like if you do the experiment, it's going to come out to be 0.77 volts. So this is an aqueous ions only electrode. So this is an aqueous ions only electrode. So it's an aqueous ions only electrode. And so you got three types of electrodes. Either the substance you're investigating is a metal. So the metal itself would be the electrode, and it will be in equilibrium with its metal ions. The metal ions would be part of the solution. Whatever happens, the potential builds up on this and you measure the potential, right? The second type of electrode is you might have a gas in equilibrium with the ions. The gas would be in a gas jar and the ions would be in the solution, and you'll introduce a platinum electrode because there is no electrode. So Cl2, if it wants to gain electrons, it needs a source of electrons. So the metallic rod would act as a source of electrons. Vice versa, if Cl-1 wants to lose electrons, all the electrons would be lost on the metallic rod. Whatever happens, the potential builds up over here. And the third type of electrode is if you just have aqueous ions. So all electrodes are going to fall into these three categories. Is that clear?
Yes.
Now, another very important point is that we did discuss this, that if you have a lower potential, which is a negative potential, that indicates a tendency to actually lose electrons. The reason the sodium electrode was so negative was that sodium really wanted to lose electrons. So there was a lot of electrons accumulating on the metallic rod, which is why the sodium electrode was highly negative. Is that clear?
Yes.
And the other rule is that whenever you have a higher potential, which means a higher potential refers to the positive potential. That indicates that it indicates a tendency to
Gain electrons.
To gain electrons. So remember, this is what we were trying to figure out, right? We wanted some quantitative value that would tell us whether the substance wants to lose electrons or does it want to gain electrons. And remember, it's always going to be a relative comparison. When I say positive, I mean, there's no such thing as, remember, when you talk about potentials, potentials are always relative. Actually, anything that you measure, that is relative to something. If you measure mass, what do you measure mass against? I mean, you measure it against a reference point, right? You measure it relative to something. Like if you go to a shop, you're measuring it relative to kgs, right? What is a kg? Kg is just some random weight. It's a completely random, arbitrary weight that someone somewhere in Europe decided that they're going to measure everything in with reference to a kg. So kg itself has no particular significance. Some countries, they measure it against pounds and stones, so they use different units. So remember this, that everything is measured against some reference point, uh, and it's all relative. For example, if you're trying to measure your height, you might be taller than someone and you might be smaller than someone, right? So it's a relative comparison. Do you get my point?
Yes.
So when you measure potentials, potentials are a relative comparison. There's nothing that is absolutely negative. There's nothing that is absolutely positive. I mean, if you measure height, there's nothing. I mean, you can't say that this is. I mean, this anyone having a height of 5.8 meters is tall, because it's a relative comparison. Like 5.8 meters compared to what? If you're comparing it to a 7-meter basketball player, then 5.8 meters is like really short. But if you're comparing it with someone who's 5 meters tall, sorry, 5 feet tall, so that is, I mean, you're going to be relatively tall, right? So it's always a relative comparison. So remember, nothing is absolutely negative, nothing is absolutely positive. It's always, so you use the term higher and lower. So when you're given two potentials, there's a higher potential and there's a lower potential. There's something that is more positive, there's something that is more negative. So let me do, so let me state this. For example, I've got two reactions. I've got Cl2 plus 2 electrons and it's in equilibrium with 2Cl minus 1. And the potentials are written as E naught. The cell potentials, the electrode potentials are written as E naught. And this value is 1.36 volts. And I have this other electrode, which is I mean, we drew the diagram, Fe3 plus 1 electron in equilibrium with Fe2 plus. And this E naught is 0 point. So if you compare the two, which one has a greater tendency to gain electrons between the two?
Cl2?
Cl2, right?
Yes, because it's more positive.
So this one is more positive. So you're going to refer to this as the higher potential. And this one, vice versa, is going to be a lower potential, right? So basically, this one wants to it wants to gain electrons, but relative to what? Relative to the other electrode. So when it comes to, so you can also state it the other way around, that this one basically wants to lose electrons. Remember, in redox reaction, if one has a higher tendency to actually gain electrons, I mean, this one has a higher tendency to gain electrons, right? So it's going to gain electrons. So the other substance would have to lose electrons. I mean, it's got no choice anymore. Is that clear?
Yes.
So just remember, this is the entire, I mean, this thing sums up the entire electrochemistry, because this is what we are looking for. Who's going to gain electrons? Who's going to lose electrons? And the potential values are going to tell us that. They're going to exactly tell us that who's going to gain electrons. The higher potential is the one that's going to gain electrons, and the lower one would therefore be the one that would be losing electrons. Is that clear?
Yes, it is.
And so now we'll come to that later on. The first thing is there'll be a lot of questions on drawings. So make sure you know how to draw. Let me put them together. Remember, there are going to be 3 types of electrodes, and they will ask you to draw a lot of these electrodes. Just a second. No idea, but let's leave it. So remember, there are going to be 3 types of electrodes. Now, so we've understood the types of electrodes. So let's focus on drawing a bit. So here's the first thing. Values electrode potentials, or any value is measured against a reference system. Are measured against a reference, against a reference point. So weight only makes sense because everyone is measuring weight with reference to or relative to 1 kg. And 1 kg is some arbitrary where everyone decided let's measure everything against 1 kg, right? How do you measure height? Let's say you're measuring the height of the building. So there's going to be a reference system. Like if you have like really tall buildings and somebody says he wants to measure the height of the buildings, right? So what they're going to do is most of the time they take sea level as, sometimes they're going to take sea level as the reference point. So here's the sea level, and all the buildings are going to be measured against this reference point. So every building will have a certain height. Some would be tall and some of them would be short. But if I change the reference point, would it affect the relative heights of the buildings or not? You get different heights for the buildings, but the taller one is still the taller one, right? What if I change? Yeah, what if I change the reference point? Let's say I say that I'm going to measure the height of the building from the deepest point in the ocean. The values are all going to change, right? But the taller one would still be the taller one, right? And the shorter one would still be the shorter one. Is that clear?
Yes, it is.
So remember, the reference point is arbitrary. It's your choice. It's something that everyone agrees to. Let's pick, like for when you're measuring heights of mountains and buildings and like heights of cities, etc., everyone has agreed that they're going to measure it because it won't make any sense. Like if somebody is measuring it against some other reference point, so like just like kgs and pounds don't make sense to us. Like, it's very hard for us to translate kgs to pounds. So if you change the reference point, it's kind of harder to switch. Same as with temperature. Like somebody is measuring with centigrade, it's very hard to actually understand Fahrenheit then. So which is why it's better to have just one specific reference point. Now what's important is when we are measuring these electrodes, just like the Fe3 plus, the electrodes that we drew earlier, let's say I'm measuring, this is a platinum electrode. So this one is made out of platinum, and I'm trying to measure the potential of this electrode. It's got Fe3 plus and Fe2 plus ions both in solution, and I'm trying to measure the electrode. So what I'm going to do is I'm going to measure the potential that's going to build up over here on the electrode. Whatever the potential is, I'm going to try and measure it. So I'm going to take a voltmeter. So it's going to be either a higher potential or a lower potential, right? That's what we are looking for. But it's going to be a higher or lower potential compared to what? Like when you measure the voltage, when you say that it's more positive or whether it's more negative, like over here, if I say this one is negative potential, but negative potential compared to what? I mean, that's the whole point. What's the reference point? So what you do is this reference, you pick one electrode and you use that to measure the potential of all the other electrodes. So if I want to say that this has a higher potential, but higher potential compared to what? That other thing where you do all the comparison with, that's your standard hydrogen electrode. All potentials are going to be measured with respect to the standard hydrogen electrode, which is basically H2 gas, and the container contains H plus 1 ions. So it contains a lot of H plus 1 ions, and there is H2 gas that's flowing in. So just remember that all your electrodes that you're going to draw, their voltages are going to be measured with respect to this particular electrode, which is known as the standard hydrogen electrode. So either your electrode will have a higher potential compared to this, or it's going to have a lower potential compared to this. So the voltages that you're getting are basically the voltages compared to this reference system. Is this clear, Rajani?
Yes.
It's just like measuring the heights of a building. You make a point. So either the height is going to be in the positive direction, you're going to be taller, or the height is going to be in the negative potential, or you're going to be smaller than that. So that's your reference point, and everything would be measured according to this. So that's hydrogen gas coming in. This is a platinum electrode. And the equilibrium that is set up over here is 2H plus 1 plus 1 electron, plus 2 electrons, sorry. And that's an equilibrium with H2 gas. So that's the equilibrium that is established over here. And the equilibrium that is going on over here, it's Fe3 plus, which gains 1 electron, and in equilibrium with Fe2 plus. So you've got these two electrodes going on. So every electrode that you drew earlier, its potential is going to be measured against this reference electrode. And there is one more thing that needs to be, one more thing that's important. And that is, so that thing is, one second, this entire thing is known as an electrochemical cell. And I'm going to come to that. There's going to be a salt bridge that is always going to be there. That salt bridge is very important for completing this circuit, and I'm going to explain that in a short while. But there's going to be a salt bridge in the middle. And that's about it. Now coming to this point, so Raji, is the first thing, is the idea clear that all electrode potentials are going to be measured against the standard hydrogen electrode? Is that clear?
Yes, that's clear.
What do you think is the potential of the standard hydrogen electrode? What voltage would this have?
Around 1.
0?
0.
It's going to be 0 because look at where's the sea level example? Like what height do you give to the sea level? You give it
0.
0, right? Because that's your starting point. You're measuring everything against that. So that reference thing is always assigned 0. And every other thing is then either going to be higher than that or it's going to be lower than that. So this one has 0 voltage. So when I say that the iron electrode is when I say that the E naught for this one is 0.77, that means that this particular electrode over here has a higher potential compared to this one. I mean, this is 0.77 volts, so this one is 0 volts. Is that clear?
Yes.
So the first, and what's the purpose of the salt bridge? That is another question. So let's bring in some physics. This one is 0 volts. So that's your lower potential. And this one is higher compared to the reference electrode. It's 0.77 volts, right? So which electrode is the higher one? It's this one that is the higher one, right?
Yes.
Now you have a potential difference between the two electrodes. You got this electrode, you got this electrode. Where do you think electrons flow towards? Do they flow towards the higher one or do they flow towards the lower potential?
Low potential.
Electrons, would they flow towards positive or would they flow towards negative?
They were positive, so higher potential.
So they're going to flow towards higher potential. So now what's happening is there is current flowing and the electrons are flowing towards higher potential, right? So the electrons have started flowing in this direction. And there's a current that's flowing. So remember this, electrons, and this would vary if sometimes the zero voltage, sometimes there's going to be negative potential over here. And this is going to, so the electrons, remember, would always flow towards the higher potential. So you would always have to check which one is the higher potential. In this case, because it's a relative comparison, in this case, this is the higher potential. But sometimes this is also going to be the higher potential. So the electrons can flow in the other direction as well. So we'll do that example next, but let's write this point that electrons flow towards the higher potential. So you're going to determine which one is the higher potential. So electrons flow towards higher potential. Now the other thing is that okay, we've got so the other thing is we've got this happening. Now previously this was an equilibrium reaction. Now what do you think when electrons start flowing in this direction? This electrode is going to get a lot of electrons. So focus on the equation. So remember, it's getting a lot of electrons now. So what do you think will happen? Where would the equilibrium shift if it gets a lot of electrons? Forward or backward?
Backward.
If the quantity of electrons increases, let's
Would
say
a
if
little bit forward will decrease? No, forward will, yeah.
it's going to be forward, right?
Yes.
Because it's getting a lot of electrons. Electrons are flowing in this direction, so it's getting a lot of electrons, right? So remember that there's no longer going to be an equilibrium. The equilibrium has gotten disturbed because this electrode has started sending electrons to this one. So it's getting a lot of electrons. So if the concentration or the quantity of a substance increases, the equilibrium would try to decrease it. So it's going to move in the forward direction. What's going to happen over here? This electrode is losing a lot of electrons. So the quantity of electrons on this electrode is becoming lesser and lesser. So this one is losing a lot of electrons. What do you think will happen? Where would the equilibrium shift if the electrons decrease?
Backward.
So it's going to try and make more electrons, right?
Yes.
Because all the electrons are traveling to the other side, which is the higher potential. So the electrons are getting pulled to that side. So the quantity of electrons are decreasing. So the equilibrium would shift backwards. So now the reaction is no longer a reversible reaction. It's this one is gaining electrons while this one is losing electrons.
Electrons.
So this one gains electrons and the other one loses electrons. And this is exactly what we studied. What did we study? That the higher potential is the one that, what does it do?
Gains electrons.
And the lower potential is the one that
Loses electrons.
loses electrons. So you don't have to go into a lot of detail. Just remember this fact that the higher potential is the one that's going to gain electrons. So if you have two electrodes, the higher potential is the one that would start to gain electrons. So it's going to go in the forward direction. And the lower potential is the one that would lose electrons, right? So, I mean,
Yes.
that's the rule. So the first thing is whenever you connect, and you can connect any two electrodes together. I mean, if you want to measure the potential, the electrode potential, then it should be, I mean, the electrode must be connected to the standard hydrogen electrode. But otherwise, it could be any two electrodes. Like if you're not interested in measuring the standard electrode potential, then you can actually connect any two electrodes together. Is that clear?
Yes.
But the idea would be exactly the same. The higher one is going to gain electrons, the lower one is going to lose electrons. Just memorize that. Higher potential gains and lower potential, it loses. But the drawings are important. And why is the salt bridge there? The salt bridge has a purpose. And the purpose is, look what's happening over here. This reaction is going in the backward direction, right? It's no longer an equilibrium reaction. It's going in the backward direction. Is that clear?
Yes.
So when it goes in the backward direction, what ion is it producing? It's producing a lot of H+1 ions, right?
Yes.
So the solution will have more and more H+1 ions getting produced. So what do you think will happen if there are too many H+1 ions produced? Will the electrons which are flowing to the other side, there's a lot of positive ions over here. So the electrons will stop going to the other side. The electrons will get attracted back. Is that clear?
Yes.
So the current would stop and the reaction would stop. Everything would stop if you have too many H+1 ions. So remember, your reaction is going in the backward direction, but in the backward direction, a lot of H+1 ions are being produced. And if you have a lot of H+1 ions getting produced, that means the current would stop. Do you get that point?
Yes, I do.
What the salt bridge does is that it provides a diffusion channel. If there are too many H+1 ions, the H+1 ions would get absorbed by the salt bridge. So all these H+1 ions, they are going to get absorbed by the salt bridge. So all of them would start getting absorbed by the salt bridge. So the salt bridge kind of acts as a balancing act. It doesn't let the ions increase in concentration. Is this clear?
Yes.
So the current would continue to flow. Even though more H+1 ions are being produced, but the current would continue to flow. So remember how to draw a good diagram. So I'll just give you some random, try and measure the electrode. One of them should be the standard hydrogen electrode. So the task is to draw a couple of them. You can draw the copper ion, copper electrode. So there's a copper electrode in equilibrium with copper ions. Its value is 0.34 volts. So that's the first one. Draw the whole diagram. Like, draw the electrode. Remember, it's a metal with aqueous metal ions. So one of the electrodes would be this one, and the other one would be the standard hydrogen electrode. The second one is, let's say we have, let's do Cl2 plus 2 electrons in equilibrium with Cl minus 1. And the E naught for this one is 1.36 volts. So draw this one as well. It's a gas and aqueous ion electrode connected with the standard hydrogen electrode. Is this clear? So I'm going to share the board link as well, just a second. And we can continue tomorrow then. Just a second, let me. Okay, so let's continue tomorrow. Do you have any questions on this?
No, sir, it's fine.
So I've sent you the board link as well.
Yes, I've received it.
Okay, then take care.
Okay, bye, sir. Thank you.
Bye bye.